everyone to our final presentation on our AI Ops system from data to action. We are Team 1 and we are very excited to walk you through our journey on implementing this system today. And these are our team members, Kong, Ben, Jermaine, myself, Eliora, Hester, and Yanjie.
Possible to unmute?
Oh, whoops, okay. But yeah, it was just a quick introduction, so yeah, I'm not missing much. Okay, so for our agenda today, we'll be going through the project overview, project management, system architecture, our 2 refinements on our ARIMA anomaly detection, event correlation, and root cause analysis. Then we'll also look at how the front end looks like for the dashboard and user testing, as well as the dashboard walkthrough, and also going through the impact and mean time to detect, and scalability, as well as future plans for integration. Okay. So to go through the project overview, this is what we were doing for. So like the problem we set out to solve is how might we build an AI ops framework for OCBC that leverages AI intelligence, artificial intelligence, time series analysis to proactively detect and diagnose IT system issues across distributed systems. So the problems that OCBC currently face is that there is an overwhelming number of unclear alerts that hinder effective prioritization and response. Fragmented signals also make it challenging to pinpoint the main issues, and reliance on manual root cause analysis makes it this whole process very slow. So our system aims to understand how these problems can be solved in OCBC. We wanted to build a 3-part e-commerce proof of concept, with the aim to reduce mean time to know and mean time to diagnose through anomaly detection, event correlation, and LM-powered RCA, which was initially a stretch goal. As for the key project activities that we conducted, we first started with our dataset creation, which involves order management system, deployment logs, and system matrix. And then we topologically aligned it with our system architecture. We also created a C1 and C2 diagram to help visualize how our system can work together, like the individual components, and then also SuperBase for which we use as our database. Before feeding all this into like the anomaly detection, where we export isolation forest, ARIMA model, and the iterations. We also look at the correlation and root cause analysis, which we export initially a V3 small language model, but before eventually settling on a Gemini 2.5 Flash LLM. We also did a dashboard where we also went through prototype, user testing, and refinements. Can you see that? I cannot see this. Yeah, I'm not looking at the slide. In the team.
Yep, now we can see this point. I just almost like not present anymore.
Sorry.
Okay, no problem.
So like how did we conduct all these key project activities? We looked into the we have a look at our strategies for project management. So what worked was like having a waterfall with iterative refinement, where there's sequential phases reflect each model iteration and within each phase, so it gives us that kind of flexibility to improve like the different components. We also did bi-weekly check-ins with our professor and also the client OCBC, so this helped keep our scope aligned as well. Then we also use RACI matrix and our meeting logs for clearer accountability. We showed the clear ownership of each deliverable within like each weekly Fridays syncs. We also ensured that shared documentation in our Google Drive also helped to keep everyone aligned, because we are often working on different components. So what we learned is that what can be improved is definitely that perhaps we could have allocated more resources earlier to synthesize the data, because like initially we just didn't anticipate that there will be that extra time. So we could have dedicated more team members upfront to accelerate this. We also should have increased like more task concurrency within each phase, so it helps to move things along faster. And then as well as like initially we didn't have a user testing, but upon consulting Prof and also like the Sakti, we also decided that user testing will help make the dashboard better for the as an end result. And lastly, we also could have predefined our pipeline integration a bit more during the proposal, because without that much like details, we did struggle initially with how we wanted to integrate everything. And then to go through like our system architecture. So like how the model simulates how like 3 interconnected systems like in banking context manage transactions. So the first we can look at like our order management system, which contains the flow of like order placement to fulfillment. So key metrics that we look into in this system includes payment failure rates, pending order counts, fulfillment failure counts. So these metrics help to ensure that smooth operations can quickly identify bottlenecks. Next, we also have a payment gateway system, which is crucial for processing payments, and the important metrics to monitor here is the retry rate and also like the latency at 95 percentile and timeout rate. And lastly, we have inventory management system, which ensures that which looks at how stock levels are maintained in the hypothetical e-commerce system. So the general happy path for like the order begins with customers placing an order, followed by the PGS for payment, and then back to OMS, and finally to IMS to reserve the inventory when payment is fulfilled. So issues can occur along these lines of like this happy path. So for this proof of concept, we explore 4 of these different problems that could occur. So our 4 anomaly scenarios mirror like that of banking incidents, which can significantly impact service reliability. First, we have the payment gateway timeout cascade, and this occurs when there's a spike in latency or timeouts within our payment gateway system, leading to a ripple effect that causes order failures in the order management system. The root cause here is payment gateway itself. So the next is phantom inventory overselling. This happens when the inventory management system allows stock levels to go to negative due to concurrent reservations. And the root cause here is inventory management system. For the second one, stock reserved without payment. Is when a stock is reserved even when payment fails, and this is due to a bug in the OMS system. And finally, for the 4th anomaly scenario, we have database query degradation. So here is when the order management system experiences an increase in the duration where it takes to retrieve like from the DB logs, and the main issue is from like if you were to push a deployment log, which causes an issue.
Okay, so now we'll be talking about the changes that we've made for the anomaly detection model since the midterm presentation. So we made 3 main changes, mainly to improve the reliability, simplify the model stack, and to fix a crucial bug that was being silenced. So firstly, the data layer is now centralized. All data sets are being retrieved from Supabase. This allows for the demo data set to auto-update whenever the simulator runs. Secondly, we simplified the detection model and removed the LSTM, autoencoder, and TensorFlow dependencies and it's now being only using the simple autoencoder. And thirdly, we fixed a score normalization with the detectors by applying a sigma normalization within each detector, and it addresses the issue of the inflated ensemble scores, resulting in a more accurate anomaly detection. So for the centralized data layer, every component now reads from a single source of truth, which is Supabase. So there will be no more local file dependencies that drift between environments. So initially, it was fetching training data, updating the demo subset, and storing results. Everything was done locally. So now it's all done with a paginated API. So when the streaming script runs, it will auto refresh on Supabase with every simulator run. And with all the data being on Supabase, it also makes the process more seamless, as the updated rows will be consumed by the next step, which is correlation and RCA. Secondly, we simplified the model due to incompatibilities with Python and TensorFlow. The LSTM autoencoder fails silently, returning random scores instead of raising an error or simply crashing. This meant that the ensemble scorer was receiving meaningless noise from the ISTM encoder on every run. TensorFlow also added significant complexity for the installation steps, and for a component that was not working correctly, and it was not entirely necessary for our use case. So we decided to only use simple encoder, autoencoder, as it does not have heavy dependencies, where it does not use neural networks, so no TensorFlow will be required. It is also better fit for the anomaly type that our model is using, which is the feature space outliers rather than temporal sequences. And it's also deterministic in training, so there will be no random initialization and no training variances between each run. Lastly, we had a fix for the score normalization within each detector. So the issue was that each detector in the ensemble was giving out raw scores instead of a value between 0 to 1. So for instance, a single raw score of 12 in one detector would push the weighted average above 0.5, even if all of the detectors reported normalized values. So this would cause normal rows to be flagged as anomalous, even though it is not supposed to, due to the skewed ensemble score. So the fix for this would be to add a sigmoid normalization in each detector. So it will be centered at its own threshold, mapping out all the outputs to a consistent 0 to 1 range. And it also has a threshold aware mapping, where the z-score exactly will be at the detectors. The detector's threshold maps to 0.5, and if the score is seen as anomalous, it will be pushed towards 1, and if it's not, it will be pushed towards 0. Lastly, we also removed a redundant double normalization, which was masking a true signal, and eliminating this would accurately show the anomalies for each row. So by streamlining this process, we've significantly improved the accuracy and reliability of our anomaly detection system.
So now I'll be taking us through the improvements in our event correlation and root cause analysis. So firstly, for our event correlation, we have moved from a single order analysis to multi-metric multi-order pattern detection with quantified confidence. So to achieve this, firstly, we have enhanced our data set level reasoning, where we analyze our core data set and deployment log as a structured context compared to analyzing logs only. Secondly, we have also improved our anomaly grouping, where our system can identify 2 to 6 orders in the same time frame instead of identifying anomalies one order instead of identifying single order anomalies. And thirdly, we have also introduced multi-metric pattern detection, where we analyze latency, timeout rate, and retry rate altogether for correlation instead of analyzing each of them individually on their own. And on top of this, we also have more precise anomaly detection, moving from monitoring milliseconds of baseline to detecting seconds of query durations, which are approximately 100 times increase in detection. And lastly, we also have quantified confidence scoring, where we now have correlation confidence score and component scores for consistency, deviation magnitude, and evidence density instead of only having correlation confidence score. Moving on to our RCA improvements, we have moved from isolated event analysis to end-to-end causal tracing with deployment context. And to achieve this, firstly, we have precise temporal root cause linkage, where we are now using a ±2 hour deployment window to correlate incidents with recent deployments. And secondly, we now have defined confidence scoring thresholds of 3 tiers, high, medium, and low. And thirdly, we also now have increased evidence coverage, where we are now processing 500 logs and 100 orders per correlation group. And on top of this, we now have clear system level attribution, where our system is able to identify which system among the OMS, PGS, and IMS is responsible for the root cause. And lastly, we have end-to-end causal tracing, moving from isolated events to fully reconstructed end-to-end flow, showing how the issue develops across systems and where it occurs.
So to visualize the detected anomalies, we use Grafana, and we'll present the initial iteration of our dashboard, followed by user testing, and conclude with the final iteration and a detailed walkthrough. So first, with the initial dashboard iteration, looking at this system health level, we organize the information by technical layers instead of user workflows. And the key issue with this is that the organization confused users regarding order failures, as information was poorly categorized across the systems. And that meant that users would struggle to locate critical information, which complicated troubleshooting. Next, for the diagnostic layers, we can see that all the correlation matrices were displayed under a single tab with no scenario separation. So this meant that we needed more structured data presentation that aligns with user workflows so as to enhance the intuitiveness and effectiveness of the diagnostics. So we can see here that many systems meant too many visualizations on one screen, which made it difficult to pick up on matrix pertaining to a specific scenario. And for the root cause analysis table, there were no links to specific order IDs, so users couldn't analyze individual impacted orders. And second, ambiguous incident IDs. Although it was useful for our correlation, these non-descriptive labels provided no clarity on the incident types for the engineers. So we'll now explore how user testing can refine the dashboards and enhance usability. So for our user testing tasks, we had 4 different scenarios. The first one is aimed at to help the user identify the payment gateway system for timeout issues. For number 2, it would be to get the users to be able to successfully pinpoint the IMS for issues related to missing orders. And number 3, to analyze a specific order ID using logs to explain the issues. And number 4, to diagnose the impact of a code deployment on database performance using deployment logs. So these tasks are vital to help us to assess the usability of our dashboard. And for the measurements, we had both quantitative and qualitative criteria. Focusing on the qualitative ones, we asked questions such as, what was the most helpful aspect of our dashboard and what would you choose to eliminate? And for clarity, which aspects felt most confusing or intuitive? And the missing features, what did you anticipate seeing but didn't? Moving on to the results of our user testing, we'll focus on the positive feedback first. The causal chain highlighted the event flow in the RCA table, and that was the most appreciated feature. It allowed users to trace events leading to the root cause, and in response to the feedback, we promoted the causal chain feature in the next iteration and enhanced it further. For the scenario tabs, these tabs were dedicated spaces for each scenario. So this enhanced the user focus and speed in investigation. They isolate matrix for specific incidents, making it easier to address one failure at a time. This change responded to earlier feedback about clutter and focus issues. So the implemented tabs included overall system health, payment gateway timeout cascade, stock reserve without payment, phantom inventory overselling, and database query degradation. And lastly, what was helpful were the order ID filters. Users could filter at 2 levels, at the overall system health, where they could zoom into a specific order, and within scenario to filter and investigate a specific order within that scenario's context. This helped to reduce the time to insight significantly and replace time-consuming manual scans with quick pinpointing of information.
Okay, now on to the fixes that we did for our dashboard. So the first one was actually the system abbreviations were actually unclear, as Jermaine has mentioned, such as PGS, OMS, and IMS. So this actually appeared throughout the dashboard with no explanation, and users were unfamiliar, especially when they were first-time users or they were not familiar with the architecture. The fix we applied was to apply a tooltip on the causal chain header for the PGS, OMS, and IMS such as for PGS, our payment gateway system, OMS, order management system, and IMS, the inventory management system. The next fix we did was on the root cause, which is actually not visible immediately. This was because we had a single page scrolling for our previous iterations, and users had to scroll past the metrics to reach the RCA table. The fix we applied was to highlight a RCA summary at the top of each scenario and having the confidence score displayed prominently, for example, 95% confidence score for the impacted orders listed alongside for quick reference. Next, users were actually unsure on where to start. For first-time users especially, there were no onboarding or guided entry point which was provided. We added an introduction tab for first-time users where they can look at the how to use this dashboard guide, which provides a directed flow with a start with overall system health, select a scenario and review the metrics, followed by the RCA. Next will be the no link between issues and impact. The problem was there was no clear linkages between the system issues and business impact, where users saw a latency spike but could not explain the missing order. Our solution was to add a causal chain which now explains the business outcome at each step. For example, when payment declines with status 402, stock reserved despite failure and orders held indefinitely, with relation to each specific order IDs and timestamp included. Next will be the metrics relationships were not clearly explained. For each visualization, users will actually see two lines but did not understand what was the relationship. As for example, if you look at the payment gateway timeout rate versus latency, there was a correlation but it was not explicitly explained. The fix was to add a tooltip to show the proportion of payment requests that time out against the percentile of payment authorization latency. This helped users to interpret multi-metric charts more clearly for better analysis. So in summary, our iteration 1, the key issues that we found were all metrics were under one tab, making it a lot of the data was actually congested and was hard to find. Root cause was not immediately visible. Our system abbreviations were unclear, which we added a tooltip, and the last one, which is no linkage between system issues and business impact. For iteration 2, the fixes that we applied, we had scenario-specific tabs, each for the 4 scenarios and their relevant metrics only. A RCA summary highlighted at the top of each scenario tab. Tooltips were added, for example, PGS for payment gateway system, and a causal chain table added showing step-by-step flow between system event to customer-facing outcome. And lastly, the introduction tab, which was added with a guided walkthrough for first-time users. For iteration 2, new features were added. Firstly, the Grafana email alerts, which automatically email notification to engineers when an anomaly is detected. Incident declarations for better tracking of anomaly and for better investigation for engineers. Thirdly, the drill down navigation, which is the overall system health, scenario tab, metric visualization, and root cause analysis. This allows for faster diagnosis at every level. And lastly, the real-time simulation for our demo, which we'll go through later on, where a simulated time clock will actually will allow Grafana to refresh every 5 seconds, allowing orders to stream through the pipeline live. So the first one, the Grafana email alerts. So your email, when an anomaly is detected, it will include a summary of what anomaly has been detected and a description of what further steps the engineer should take. And they'll also include a link to the incident page where engineers can declare it as an incident. And for the MTTK impact, the mean time to know, engineers now no longer need to constantly monitor the dashboard, as alerts will be pushed into their email once it's been detected. So for Grafana alerts configuration, it uses a state-aware detection. For the alert rule architecture, in order to prevent information overload for each anomaly coming in, we actually group it into 5 strategic groups. 1 dedicated group per scenario and 1 additional group for unseen scenarios. So this reduces the noise while actually maintaining a full coverage for the anomaly detection. For the alert query logic, as long there is 1 anomaly being detected, it will be fired off to the engineers. And lastly, for the state awareness and state change, they will only fire an email alert when the state has been changed from OK to firing for the first proper scenario. If the anomaly is not resolved within 4 hours, another reminder will be fired off. So for the proof of concept workaround, as Grafana actually uses look back over time series interval, which means they actually look back at the last 5 minutes. So as our super base data is static, so we built a live simulation loop. How we actually solve this problem? We use a custom Python simulation loop to inject the anomaly data points point by point, synchronized with the advancing simulation clock. Firstly, we orchestrate the Python script and it monitors the dynamic sim time now from
sorry, just to interrupt, you go back to 10 minutes left in the presentation.
I think we lost audio. Is it just me?
no,
No, it's me actually. I was stuttering, not the video.
okay, so 10 more.
You go back to 10 minutes left in the presentation time.
Okay.
Then we have 10 minutes Q&A. So if you're going to do a demonstration, I just want to make sure you've got time for your live demo.
Okay, so we'll go to point in time match, synchronize and extract, and the live ingestion. So after declaration, which I will show shortly, so when you receive a notification in your email, this was just flagged off 1 minute ago. As you're going through your day, the notification will come in. So what you will see is a summary, for example, anomaly detected, payment gateway timeout cascade. The instructions is to view the dashboards, and once you click the link over here, you will go into the incident declaration page over here where you can declare it as an incident. So as mentioned, the payment gateway timeout cascade, where you can declare this as an incident over here for better incident tracking. As this is a critical incident, we'll label it as critical, and it's customer facing, which is customer affected, where we'll take it as a label. So this will allow for better prioritization. So once you have declared the incident, you can then go onto the dashboard to actually track the data and do a better investigation of what is happening. So now Jermaine will go through a deep dive of the dashboard.
Yeah, so we will start at the overall system health. This provides us a summary of how our system is doing now. So you can see the number of normal orders as well as the number of anomalous orders detected, payment status here, and then also the different scenarios and the orders that are being affected. So let's look into one of the scenarios. We can see here that we can zoom into the graphs, and here you can see that the timeout rate as well as the latency are correlated because they both spike at the same time. Next, we can see that there's a summary where we can see that the root cause is that it's payment gateway timeout cascade, and we can then zoom in into the causal chain. We can see the system that is being impacted. So first with the PGS followed by the OMS. If we read into it, it says that the PGS had extremely high latency and a high timeout rate. And then OMS initiated retries, and following that, it led to failures and orders were being cancelled. Looking at the incident logs, we can even filter down to a specific order, and we will observe that there's a payment timeout event with a status code of 504. This means that the engineer knows that the root cause would be the payment gateway, and they will need to, the payment gateway system, which they will need to scale or to solve. So with that, we'll go back to our presentation.
To the very last part of our presentation, we are going to quantify our impact compared to what OCBC currently have versus with our AI Ops operations. In terms of impact, we are looking at mean time to know (MTTK) and mean time to diagnose (MTTD). So currently in OCBC, we have a mixture of automated, semi-automated, as well as a manual verification. Currently in OCBC, in-house, we already have ML-driven anomaly detection. In the LEK stack, identify abnormal matrix behavior, which triggered the real-time alerts for early incident detection. After that, an engineer will actually receive an alert through their in-house IT system, HPSM, or through the email. Investigation will take place as the engineer will then now look into analyze the logs, matrix, as well as to chase across multiple tools that they currently have. And then let's say if the issue is needed to be escalated to different teams, such as application and infra team, it will then also be causing the delay and the fragmented handoffs. Last but not least, they will try to find out what is the root cause of the issue. Teams will then manually correlate the signals across the system, and often require significant time and effort as well as coordination. So in terms of the time, we estimated that for MMTK, it will estimate to take roughly around 22 minutes with 15 minutes of the ML system to run, roughly 2 minutes for the engineer to actually pick up the email and identify there is an issue coming about, as well as the engineer will then now see and acknowledge the issues. For our AI ops automated end-to-end, we will now actually almost automated the whole entire pipeline from detection to alert correlation as well as RCA, and the time is significantly reduced. The only last thing is human verification is actually our engineer to review the case and find out the root cause through using our dashboard. So in this improvement, you actually can see that for MMTK, the time actually reduced by half, from 22 minutes to actually only 11 minutes to actually see the issue and identify the issues. For time to diagnose, time also significantly reduced by 65%, from almost 4 hours 40 minutes to only now is 98 minutes, which is an hour and a half. In terms of scalability and integration, we actually come up with a variable sources of scalability for anomaly detections. With the interest of time, we won't go through it in details. And same as for RCA and correlation, we actually also have all the packages as well as the justification of why we actually go with these packages if we want to scale it out. And last but not least is in terms of the future in general with the scale direction, there's one point we want to highlight here is that we would want to have a vector DB. Why a vector DB is that it will actually record all the historical record of the abnormal incidents that we have. And then we're actually going to make use of RAG, retrievable augmented method, to actually retrieve out the enrich the root cause using the past incident records. That will be one of the that we are going to looking in if we actually want to scale it up. Followed by hybrid ML LLM architecture, streaming architecture using Kafka and PubSpot, as well as some of the cost optimization strategies. And with that, we have come to the end of our presentation. Thank you for your time and wonderful semesters.
Thanks, Tim. Yeah, I have to apologize because I wasn't reviewing.
Thank you so much. I think it's wonderfully put together, right? The way I see, very detailed. I had a couple of questions that I wanted to probably understand a bit more. Right? If you could go back to a few slides before around the root cause itself.
Do you want to see our refinement part or the our mean time to know or mean time to diagnose part for RCA?
MTTK. Yeah.
This part, the mean time to know, and so you can tell us where to stop also. Here?
Yeah, so no, one. Yeah. So, okay, this is estimated MTTK is 22 minutes and estimated MTTP is 280 minutes. How did we come to this number? Was this shared by us or shared by Lucy?
I think for this number is actually a very estimated numbers. We actually looking through the slide that you guys have in before we actually do our proposal, as well as we actually talk to Satik about the number as well. In terms of the accuracy of the number, I think we will need you to verify again. So yeah, I think we are more confident of our number in our system.
Okay.
Yeah.
Okay, and so this is based on what was shared by us to you. I understand.
Yeah.
So for your anomaly detection itself, right? How many metrics or parameters were considered? I know you do mention about 4 or 5 along with the percentiles, but in total, what sort of telemetry or count of telemetry was actually used here?
Yeah, that's a great question. Let me just pull up the slide. Okay, so we actually based on different scenarios, there's like a different sets of matrix that we are looking at. For example, if there is like for scenario one of the abnormal scenario like payment gateway time up cascade, we actually look into, for example, payment failure rate and what are some of the pending order count as well as the fulfill rate, fulfilled failed count orders. And then we actually have two numbers. So one is like a normal numbers, the baseline numbers, and one is the number that is when abnormal cases appears. So from then we actually look into.
So I think the question was more around: is it just 3 metrics for OMS, 3 for PGS, and 3 for IMS?
I think there's other more matrix as well. However, I think in the LLM, I try to focus on the matrix that is actually show out the pattern the most, because currently we actually using the free version of the LLM. So for us to scale, like we have mentioned, we have to use like a bigger version of the LLM to take in more data inputs. That's the reason why we only chosen these a few matrix to feed into the LLM to look into.
I understand now. Yeah, I think that makes sense. You used aggregation at multiple layers to work around the limitation of the volume over the element. Okay.
Yeah, that's right.
This is good.
Yeah.
In fact, the Grafana dashboard also I think is quite impressive for a project of this size, right? I think it's quite impressive in itself. So, a couple of things that I wanted to understand a bit more, right? Now, when you say in the scenario that you walked through for the root cause, where there was a 504 across the payment gateway system, in a complex organization or in a big layout, like in the case of OCBC, that's just the face of that's just the tip of the iceberg, right? What leads to the microservice under the hood that was affected? That could be multiple reasons, things like your storage itself having issues, your network having issues, or interconnecting systems having issues. So, appreciate for the scale of this project. This is fantastic. But in real life, I think this would be more to this. There's more than what meets the eye, right? There's multiple moving components, especially in a large organization like ours. We have about 5,000 to 6,000 microservices running at any given point in time, running on a lot of infrastructure as well, right? Lots of storage, lots of different network systems, and lots of different hypervisors and so on. But this is good. I think this is one of the feedback comments that I had, that while you stop at 504 as a root cause, in real life it can go much deeper into that. 504 across the payment gateway microservice is just, I would say this is one of the symptoms or manifestations of the actual root cause, which could be even further deeper down in the hierarchy.
Yeah.
I think overall well done, nicely put together, I would say. Again, I come into the call quite cold. I'm slipping in for Sakti. Sakti had an unfortunate scenario where he couldn't, his flight was cancelled, so be here on time.
Thank you for your time today.
Thank you so much. Do you have any questions for me or CBC?
I have questions for the team. I'm not sure if he can hear me.
Too many questions for them, just.
That's Sandeep.
Yes, that's me.
Hey, hi Sandeep. Yeah, this is the result. Together with Prof. Paul, we've been supervising the project together. So I'm the reviewing professor. Yeah, just a question to the team around the improvements in the MTTD, right? Mean time to diagnose. Because I think went down to 98 minutes. But I was just wondering, given that now there's AI-powered RCAs, why does it still take 98 minutes? Is it because we're not training based on an internal knowledge base that OCBC has, and therefore we still need quite a fair bit of manual engineering efforts to precisely diagnose the RCA? And related to this question, then how then can we bring it down further?
Yeah,
So this is all in OCBC context, yeah?
Right.
Yeah. So I think first things first, right? In order to have the best MTTD, mean time to diagnose, an organizational maturity and let's say monitoring maturity, observability maturity is the key. Now, where we stand in OCBC, out of all the systems and microservices, we have a lot of open systems. We have microservices, we have some legacy systems like IS484 and mainframes, right? Not all of these systems are equally observable. So a modern microservice is very observable. It's built on Kubernetes construct, right? It's CNCF, and there's multiple application performance monitoring agents running on them, infrastructure agents running on them, and so on. So there are systems which are more observable than the others, and that will be limited telemetry for systems which are closed, right? Like host systems like IS400, you couldn't really get the various speeds of telemetry that you get for, let's say, a microservice, or even a system which is running on a Red Hat, let's say Red Hat Linux with the standard Java deployment Spring Boot, or
Got it. So it's kind of we need to follow a modernization journey before we can, get the numbers to be healthier.
Absolutely. There's two things, right? One is modernization journey, and some of these are legacy regions. We couldn't get out of IS400 as soon as we like to, simply because of the robustness and reliability that has. And modernization is one of the key, and observability maturity is the key. Not all applications may be getting the same kind of radar as many applications. So if you bring all the applications to a high level of maturity, like maturity level 4, level 5, I won't go into the details of what maturities 1, 2, 3, 4, 5 are. I think if all of them are mature at the highest maturity level, then that directly correlates to your mean time to diagnose. I think this is how I would summarize this.
Sure. Yeah, thank you very much. That's very helpful. Yeah, maybe pass it to Prof.
Prof, do you want to add on the question that
Yeah, so I think your question, just to simply put, is that you're asking that with AI advancement right now, why there's still such a high time required for the time of the human interaction and checking out, right? So I think that you're actually looking at our step. Most of the steps are actually already automated by the system itself, either by ML or by AI. But then the last thing is we need the human to actually look into our dashboard to actually, first of all, to identify the situation, and we still need them to see the causal chain, because at the end of the day, the engineer will be the one who make the decision, right? So they will be the one who actually view the output of the AI. So that's why I put the time is slightly higher.
Right. Yeah, maybe just to share, because
I understand why you put a conservative number, but that's a very good rationale as well, right?
Yeah.
So we don't leave everything on autopilot, unlike an airliner, for example. A lot of it is an input from the system where some human will have to make the decision. So that's a perfectly reasonable estimation. Yeah, I would say.
Yeah, okay, thanks. Yeah, just a couple of questions for me. Just first was just on your UAT. You did UAT. How many people were involved and how many UAT testing was done? How many UAT tests?
Prof asked a question about UAT, so we are going to go through that now.
Yeah, our user testing was only with our sponsor Sakti.
Then also we did like user testing within our group. So as the dashboard is mainly made and designed by Jermaine and I, so we actually let the other 40 members to actually test. So the sample group will be about 5 people.
Okay, thanks. And just the changes. So you had a number of changes. How were they managed in terms of the impact on the overall timeline and resourcing? Did you just kind of do more work, or how did you manage those changes?
So like in terms of project management, so like I think there were a few times where like there were times where there was a bit of scope creep. Then we did analyze whether we had the capacity to, and then like comparing to what was initially agreed on, we tried to explain like this is like in terms of our timeline, and we just communicate that given that it's this week now and we need how many days to complete this, then we compromise by like only doing what is the essentials so that there is still like a sort of additional output, which is what we have now for the scalability and also like our user testing. We didn't directly get to do a A/B test, but we used a user testing and instead it was much more useful because we got like more direct feedback and iterations to follow through. Yeah.
So you kind of reprioritize those new changes to what was there
Yes.
and left some behind.
Yeah, so just clarify what is like what will make the most amount of impact and what can be accomplished within the time.
And I was agreed with the sponsor.
Oh.
Okay, thanks. Yeah. Yeah, it's good. Yeah. Okay, do we-
I think Paul, I couldn't catch everything, but I get the gist of what you were saying on the call. Yeah.
He asked a question of like when there was scope creep, how do we manage that? So that was more the project management aspect of the project, not so much like the technical details of it. Yeah, so one of the issues one of the additional requirements was to implement a A/B test. So instead of that, we did user testing. Then in terms of addressing scalability, we scoped down into what was like most useful and relevant. Yeah.
Understood.
Okay, thank you very much. Yeah.
Background noise.
Okay.
Okay.